Okay, so far in our Simplex algorithm adventures, we have considered how to use a Simplex algorithm on 2D cases, and I've shown why it works graphically. But in an examination setting, you're more likely to come across a 3D or 4D linear program, which would require the Simplex, because you can't use a graphical method for 4D and not very easy for 3D. So let's have a look at the Simplex algorithm applied to a three-dimensional case first, and then we'll also have a look at a four-dimensional problem as well. Okay, so with a three-dimensional case, we have three variables. So in this case, we've got an x, a y, and now we've introduced a z. Now, it doesn't have to be x, y, and z. You could have a, b, and c, or p, q, and r. It could be anything, depending on what it represents. But I'm going to stick with x, y, and z for this video. So then we have our objective, which is to maximize p, and then we've got three constraints here. So we're going to maximize this function subject to these three being true. Okay, so set up our initial tableau exactly as we did with our 2D case. So p on the left-hand side, you need to bring all of these variables to the left-hand side, so the coefficients will become negative. So we'll end up with a 1 there, a -9, a -12, and a -8. There's no slacks there, and the right-hand side is initially 0. Okay, so that's our objective row, putting all the variables on the left, and the right-hand side will be 0. Okay, now for these ones, we're going to change them into equations, and to do that, we add a slack variable to each of these, and then that replaces the inequality with an equals sign. So we're going to have 2x plus 3y plus 2z plus a slack equals 90. So 2x plus 3y plus 2z plus a slack equals 90. And there's obviously no p anywhere else. Okay, same thing here. So I'm going to introduce a second slack. So let's call it S2. So it's 2x plus 2y plus a z plus a different slack variable is 65. And then finally we need a third slack variable for our bottom constraint. So it's 5x's plus 2y's plus 2z's plus a third slack variable is 110. So that's our initial tableau. Okay, so what I'm going to do is I'm going to perform an iteration of Simplex on this tableau, so you can see it in action. Then I'm going to jump to the penultimate tableau, and then I'm going to show you the final iteration and then extract the solution. Usually in an examination, you'd be expected to do one iteration of the Simplex. You wouldn't be expected to do the whole thing, because it does take quite a while. Okay. So the first thing to do with the Simplex algorithm is to choose the pivot column. And to choose the pivot column, you look along the objective row and you choose the most negative number. In this case, it is -12. So that is the column that gets selected, and my pivot will occur in that column. Now we conduct a ratio test. Now, the ratio test is carried out on all the constraint rows, which is these three. And to do the ratio test, we can do the right-hand side divided by the entry in the pivot column. So 90 divided by 3 is 30. 65 divided by 2 is 32.5. And 110 divided by 2 is 55. Okay, now from the ratio test, we want to move from the origin, but we don't want to overshoot. We don't want to leave the feasible region. So we must choose the smallest positive result from the ratio test. So that in this case is 30. That ensures that we remain within the feasible region. So therefore this will be my first pivot value. Okay, now we can actually do an iteration of the Simplex algorithm. So what I'm going to do is on the left hand side, I'm just going to write down the instructions for each of these. As usual in previous videos, I'm going to refer to the previous table as R1, R2, R3 and R4 for my 4 rows. I'll also be using PI, which would refer to the pivot row of the new table. Okay, so PI is this one, and that is going to be defined as row 2 divided by 3. Okay, so it's row 2 of the previous table divided by 3, and that just ensures that our pivot entry is the number 1. So that's going to remain at 0. Then we've got 2/3 there. That's the number 1. That's a 2/3. That's a 1/3, that's a 0, that's a 0, and that is a 30, the result from the previous ratio test. Okay, now I need to add multiples of this row to the other 3 rows so that everything else in that column is a 0. So row 1, the top row, is going to be the previous row 1, and I'm going to add 12 times the pivot row. Okay, so row 1, that's row 1 of the previous table, plus 12 times the pivot row, which is this row here. And that will ensure I've got minus 12 plus 12 times 1, which will make that entry 0, which is what I want. Let's put the instructions down for the other ones. That's going to be row 3. This I'm going to subtract 2 times the pivot row. And then finally, row 4. This is also going to be subtract 2 times the pivot row. Okay, so those are my instructions over there. I can fill out some of these quite quickly. So this is going to be a pivot column, so it's 0, 1, 0, 0. P column is always that, and that never changes. And then the other 2 columns that aren't going to change are these 2, because this column 0, 1, 0, 0 is moving to Y. That means that these 2 will be the same, because I'm adding multiples of 0 to the other rows. So that's a 1, a 0, a 0, a 0, a 0, and a 1. Okay, so those are the ones I can fill out nice and quickly. And I've now got 4 columns, 3 rows left to fill out, which I'll need to use these instructions to do. Okay, so first one, we're going to have minus 9 plus 12 times 2/3. So that's minus 9 plus 8, so that's minus 1. Then we've got minus 8 plus 8, which is going to be a 0. Then we've got 0 plus 4, so that's going to be a 4. And then we've got 0 plus 12 times 10. So that's 100 and... nope, sorry, that's going to be 0. But let's just use a calculator. It's so much, so easy to make a mistake with this. So this is going to be 0, which is the previous R1 entry, plus 12 times the pivot row entry, which is 30. Here we go, 360. Okay, let's use a calculator from now on, just to make sure I don't make any silly mistakes. Okay, so this is row 3, subtract 2 times the pivot. So that's 2, subtract 2 times the pivot, which is 2/3. That comes out as 2/3. And then here, this entry is going to be the old row 3, which is 1, subtract 2 times the pivot entry, which is also 2/3. So that's going to be negative 1/3. And I've got 0, subtract 2 times 1/3. And then I've got 65, subtract 2 times the pivot entry, 30, just 5. Okay, and then finally row 4. So row 4 is the old value, subtract 2 times the pivot value, which is 2/3. That's going to be 11/3. And I've got 2, subtract 2 times 2/3, which is 2/3. 0, subtract 2 times 1/3, which is negative 2/3 again. And then finally 110, subtract 2 times the pivot, which is 30. That leaves me with 50. Okay, so there's my first iteration of the Simplex algorithm. Obviously in the exam you wouldn't have the luxury of different colours, so just be really careful with making sure you're adding and subtracting multiples of the correct row. In this case it was this row. Okay, so now I'm going to give you the next iteration. So this is the table after a second iteration of Simplex. And we know we're not at the optimal vertex yet because there is still a negative in the objective row. Okay, so here, there's a negative here. So that's why this column X was chosen as our pivot column, which is why it's now a 1 and 3 zeros. But we're not the optimal vertex because there's still a negative in the Z row. So we can make improvements on this right-hand side by choosing Z as our pivot column. So let's do the third iteration. Conduct a ratio test. So that's going to be the right-hand side divided by the pivot value entry. So that's going to be 25. 7.5 divided by negative a half is negative 15. But we can actually ignore that because it's negative. And then 22.5 divided by 5 halves is 9. So the smallest of those, which is positive, is this one. So that is our chosen pivot value. Okay. So that essentially means I want to make this column look like 0, 0, 0, 1. The P will remain as 1, 0, 0, 0. X and Y are the other two pivot columns. So they will remain as 0, 0, 1, 0 and 0, 1, 0, 0. Okay, so to get to this new row, we're going to divide everything in that row by 2.5. So the pivot row, okay, PI is now defined as being row 4 divided by 2.5, which is the same as timesing by 2/5. Okay. So 3 multiplied by 2/5 is 1.2. Minus 11/2 divided by 2/5, sorry, times 2/5 is minus 11/5. Minus 11/5. Better keep things as fractions. 1 divided by 5/2 or 2/5 is 2/5. And then that's the value of the ratio test from before. And now for the instructions. Okay, so we need to get rid of this. So we're going to do row 1 plus the pivot row times 1/2. So I'll get rid of the 1/2 there. This one here is going to be row 2 subtract the pivot row because it's just the number 1. This one here, we've got to get rid of a negative 1/2, so that's going to be row 3 plus the pivot row times 1/2 again. Okay, so those are my instructions over there on the left. Okay. Alright, get the calculator out again. Row 1 plus the pivot row times 1/2. So row 1 was the number 3 plus the pivot row, which is 1.2 times 1/2, gives me 3.6. If I just do this column, then I'll just pop the rest down. So row 2 minus the pivot. Row 2 was the number 1. And subtract the pivot, which is 1.2. So that's negative 0.2. And then row 3, which was the number negative 1. I'm going to do plus the pivot row, which is 1.2 times 1/2. So that comes out as minus 0.4. If you fill out these instructions on the rest of these 9 numbers, we'll end up with 0.4, 1.2, and 0.4, 0.2, minus 0.4, and 0.2. And the right hand side is 3, 7, 2, 16, and 12. Okay. Now we have reached the objective vertex of our feasible region, and we know that because, let's look at our objective row, there are no negative values left here. So that means we are at our objective, our optimal vertex. To extract the solution, we can set S1, S2 and S3 to 0 because these are 3 columns that are full of junk. So S1 equals S2 equals S3, which equals 0. And then that leaves P as being 372. X is 12. Y is 16. And Z is 9. And that's the optimal solution to the linear programming problem. So hopefully you can appreciate that that is very similar indeed to the 2-dimensional case. It's just now we cannot visualize it because it's in 3 dimensions. Okay. Let's have a look at a 4-dimensional problem. We'll just do this to wrap up the video. What we're going to do is we're going to extract the initial tableau and then going to give you a tableau that was performed later on in the algorithm, and then we're going to complete one iteration of this. And that's a fairly common way that an exam will assess this. It allows you to write the initial tableau, but yet if you make a mistake in this, you're not going to be penalised again because they then give you a later tableau for you to perform an iteration. Okay, so that's quite a common examination strategy that the exam writers use to assess this. Okay, so four-dimensional case. So we've got our x, y, and z as before, but now we've got a w. So that's our fourth variable, w, x, y, and z. And now there's no way to visualize this because we live in a 3D world, so you cannot graph this very easily at all, let alone visualize it. So it is down to Simplex to solve this problem. But we're going to just do exactly as we've done for the two-dimensional and the three-dimensional case. This objective line will go in the top, and then we have a for constraint, which will go here, introducing our four slack variables, one for each constraint. Okay, so the top one, P, all of these are going to come across the other side, so they're all going to be negative. So negative 2w, negative 3x, negative y, minus 5z, and that's going to equal 0. So 1, negative 2, negative 3, negative 1, negative 5, and then all the rest are 0 because there's no slacks in the objective. And that leaves us with 0 initially on the right-hand side. All the rest of those are 0 because P doesn't occur anywhere else. We're going to replace this less than or equal to with plus a slack and then an equals. So we have 1w plus a 5x plus a 2y plus a z plus a slack, and that is going to equal 161. Then we have 2w and 5z plus a slack equals 157. 5w plus 2x plus 5y plus 0z plus a slack is equal to 170. And then finally our z must be equal to 25. Or the z plus a fourth slack equals 25. So that's the initial tableau from the new program. That might give you 2 or 3 marks in the examination, okay, without having to actually perform Simplex. Okay, so at some point in the algorithm, we don't know, it's still told after 2 iterations of the Simplex, we end up with this tableau. So here's our tableau after 2 iterations, and we are asked to complete another iteration, explaining why 1 is needed. Okay, so let's just explain verbally why 1 is needed. Have a quick think. Okay, so 1 is needed because if we look at our objective row, we have a negative number. So because there is a negative number in the objective row, we need to do another iteration of Simplex because we have not arrived at our optimal vertex. So that is the only negative number, so therefore that is the column that is chosen for our pivot. And we now need to conduct a ratio test. The ratio test is carried out on all the constraint rows, don't do it on the objective row, and it is this right-hand side divided by this value here. So we're going to have 136 fifths divided by a fifth. Well, that's just going to be 136. 32 divided by 2, that is 16. 578 fifths divided by 23 fifths. Now that one I cannot do in my head. So 578 fifths divided by 23 fifths is 25.1. And this is 25 divided by 0, which is infinite. So the smallest positive value is this one here. So that one is the one we're going to move in. That's the direction. So this is our chosen pivot. Okay. Excuse me. So we have a blank table ready to carry out our iteration. P will always be 1, 0, 0, 0, 0. We want to make this column 0, 0, 1, 0, 0, and that's going to be defined as the pivot row, and that is going to be row 3 divided by 2. Okay, so third row on the previous tableau divided by 2, that makes that a 1. I can then fill out the rest of that row very quickly. So that's going to be a 0, a 0, a 0, a 0. That's going to go to a half. That's going to remain at 0. That's a minus 5 halves. And that's going to be 16. Okay, the other ones I can fill out really quickly are the 3 pivot columns, which are not 0, 0, 1, 0, 0. So that's the X column, the Z column, and the S3 column. So X is 0, 1, 0, 0, 0. Z is 0, 0, 0, 0, 1. And S3 is 0, 0, 0, 1, 0. Okay. So now we just have to fill out these 1, 2, 3, 4, 5, 20 elements. Okay, and to do that, we're going to fill out our instructions as before. So we've got the rest of this column. We want to make all of that at 0. So the first instruction is going to be row 1 plus the pivot row times 7/5. That will get rid of that. The next one is row 2, subtract the pivot row times 1/5. The next row is row 4, subtract the pivot row times 23/5. That's going to be fun. And this one's already a 0, so I can just put row 5. So actually I can just copy that row down straight away because nothing's going to change there. 0, 0, 0, 1, 0, 0, 0, 1, 25. Okay, that speeds things up a little bit. Okay, right, so let's do all of these. If you want to pause the video and have a go yourself, then now is the time to do so, and then you can check your answer once I've done it. Okay, so row 1 plus pivot times 7/5. So the pivot is 0 here, so actually it's just going to be row 1, which is 5th. And that's because it's already a 0 in the pivot row. There's actually a 0 here as well, isn't there? Well, that does make this a little bit quicker, which is nice. So I'm just doing 3/5 plus 0 times half. So that's going to remain as 3/5. And in fact, because those two are 0, everything else is going to remain the same as well. So that 2/5 is going to remain as 2/5. That 21/5 is going to remain there. That 5th is going to remain there. And that minus 2/5 is there. Because I'm adding multiples of 0. So that makes that nice and quick. Okay, that's worked out all right, isn't it? So now I've only got 1, 2, 3, I've got 9 values to work out. Okay, so the previous value was a 0. Plus the pivot row, which is a half, times 7/5. So 1.4. So that's 0.7 or 7/10. And the next one, the previous value was 22/5. Then I'm going to add 7/5 times the pivot row value, which is minus 5/2, which is 9/10. And then finally, this one, 1033/5 plus 7/5 multiplied by 16, which is 229. Okay, next row, R2, which was a 0, minus 1/5 times the pivot. That pivot value is a half, so that's minus 0.1. Minus 1/10. And then the next one is minus 1/5. Minus 1/5 times the pivot entry, which is minus 5/2. So that is 3/10. And then the final entry over here is 136/5. Subtract 1/5 times the pivot entry, which is a 16, which is 24. All right, and last row to do, row 4 down here. So it's row 4, subtract 23/5 times the pivot. So row 4 was a 0. Subtract 23/5 times the pivot, and the pivot was a half. So that's minus 2.3. Which is not what I got over there. So I'm going to try that again. 0, subtract 23/5 times a half. No, it's minus 2.3, yeah. So I'm going to write that as minus 23/10, just because I've got everything else in fractions, but minus 2.3 is also fine. Row 4, so that was 2/5. Minus 23/5 multiplied by the pivot element, which is minus 5/2. just be really careful with your signs. Okay, that's why I recommend writing these down as instructions to the left, so you can see exactly what's going on. That was 119 tenths, and then my final entry here is 578 fifths. Subtract 23 fifths times the pivot entry, which is 16 at 42. Okay, so that's my final answer for the next iteration of Simplex. And again, we can see that we are at the optimal vertex now because there are no negatives in our objective row. So we can extract our linear programming solution. Let's take the LP solution. The solution to this linear programming problem is P is equal to 229, and this occurs when X equals 24, W equals 16, Y is a column full of junk, so Y is 0, and Z is 25. Okay. All right, so that is that's that. So hopefully you followed that okay. If you have any questions, then please just pop them in the comments below, and I'll get back to you. But hopefully that was all okay for you. Thanks for watching, and check out some other videos if you're still learning things to do with Simplex.